Thomas Edison started it all for General Electric 120 years ago with the invention of the electric light bulb. His bright idea established the need for the utility industry and for the nuclear power industry. And since then, General Electric has been bringing good things to life. We're proud of our company's heritage. General Electric has become a symbol of quality to customers around the world. Today, this dedication to quality can be found in the world's most modern nuclear fuel fabrication facility in Wilmington, North Carolina. Since production started at Wilmington in 1968, we've developed and implemented high-technology fuel manufacturing and quality control processes. We've modernized our capabilities through major investments in automated equipment and processes. General Electric has confidence in the nuclear industry and in the long-term role for General Electric in our industry. In our fuel factory of the future, each automated unit operation performs three functions essential to modern manufacturing: manufacture, measure, and report. Automated absorber rod manufacture is an example of the combination of these three steps in one unit operation. This is a boiling water reactor control blade. It's about 5 meters long and is made up of 84 individual absorber rods. Each absorber rod is a stainless steel tube, 5 millimeters in diameter and filled with boron carbide powder. About every meter along the tube, a steel ball is dimpled in place to limit powder migration. An automated manufacturing station has been designed and built to manufacture, measure, and report on absorber rods. The critical design parameters for an absorber rod are boron density, zone length, and diameter. A computer-controlled mechanism locates the balls magnetically and dimples each one. The absorber length between dimples is measured, and a sample of the finished rods is scanned with a gamma densitometer, an ultrasonic wall thickness gauge, and an eddy current diameter gauge to determine boron density, zone length, and diameter. The data from the three measurements are collected in real time by the station computer, which then instructs the station automatically to sort the absorber rods into accept or suspect output bins. The inspection data are then presented by the computer for ready reference or for archive storage in quality information systems. Automated absorber rod manufacture and inspection provides the highest assurance available that control blade specifications will be met. Zirconium alloys are pyrophoric, so all of our fuel cladding, channels, and other zirconium-bearing components are manufactured in this separate building. Fuel bundle channels are formed from zirconium sheet and then welded and heat treated. Our automated channel heat treatment station is a high-technology metallurgical process used to inhibit channel corrosion, improve creep resistance, and increase channel life. In this process station, a heat treatment zone is passed down the entire channel length using automatically controlled and monitored induction heating. Heat up rate, soak time, and quench rate are closely controlled during heat treatment. The station computer controls and monitors the process, makes corrections, and creates permanent records of a dozen process parameters used for future design improvements. Last year, General Electric fabricated 110 million nuclear fuel pellets, 300 10-gram pellets for each boiling water reactor fuel rod. Each pellet was inspected to assure integrity of the heat transfer surface. An automated pellet inspection station has been installed which manufactures, measures, and reports on each pellet for dimensions, integrity, small cracks, chips, and other properties which might affect heat transfer performance. This automated station consists of a grinder to size pellets, 2 laser inspection systems, and a mechanical handling system which sorts the pellets and stacks them onto trays. The pellets are ground in a dry centerless grinder to diameter tolerance within 1.5 mils. They leave the grinder at a rate of about 3 pellets per second and proceed in a column to the laser inspection system. Here they're queued up to be pushed past lasers which scan them in batches of about 17. One laser measures diameter and length and checks chamfer dimensions, and the second one looks at the heat transfer surface itself to inspect for chips, cracks, and other imperfections. The laser scanners produce digital data at about 2 megahertz rate. High-speed microelectronic circuitry then process the data into a real-time accept or reject decision. The machine sorts the pellets, collects the acceptable ones in columns, and automatically loads them into trays. There they're weighed automatically and readied for the next manufacturing operation. Weight data for each tray are transferred to the plant material inventory system. Pellet reject data are used to monitor the grinding and ceramic processes. Automated pellet inspection is another example of the factory of the future, where 3 manufacturing functions are combined in one automated unit process. Every boiling water reactor fuel rod is uniquely serialized for traceability during manufacture and after reactor performance. People read and record these serial numbers at 8 different manufacturing and inspection stations throughout the factory. Because people make reading or transcription errors about 1% of the time, we've developed a machine that reads the serial numbers with greater reliability. General Electric's automated fuel rod serial number reader can read stamped metal better than people can, and it almost never makes a mistake. The first use of the serial number reader is a computer-controlled robotic end-plug stamper and quality control station. A vibratory bowl feeds each end plug to a robotic arm. Photoelectric sensors on either side of the plug alert the robot to pick it up and place it into a standard industrial metal stamping machine. Here the 7-digit serial number is heavily stamped so it can be read throughout the factory and after reactor service. Next, the robot delivers the stamped end plug to the serial number reader, where it's read by machine and reported to the unit microprocessor. The microprocessor checks the number for readability, consistency, and duplication, and reports to the factory's information system a new batch of unique machine-readable fuel rod end plugs. The success of the fuel rod serial number reader has pointed the way to other industrial applications for serial number reading technology. Successful demonstrations on tires, integrated circuits, and on stamped metal products have led to a new industrial product line for General Electric. Image processing and recognition systems are on sale inside and outside the nuclear industry for factory automation applications. As a final example of automated equipment for the factory of the future, I've selected General Electric's unique fuel rod inspection system, MAPS, the magnetic and passive scanner, which provides the final quality control in the manufacture of gadolinium-bearing fuel rods. MAPS measures the exact uranium and gadolinium content of every pellet in every finished fuel rod. The gadolinium measurement is based on a unique patented gadolinium sensor, a superconducting magnetometer. Fuel rods are transported along the axis of a superconducting solenoid. Small pickup coils inside the solenoid respond to changes in the magnetic moment of the fuel. Since gadolinia has a higher paramagnetic susceptibility than urania, the gadolinium content of each pellet can be measured. With simultaneous measurement of fuel density, the gadolinium content can be determined to plus or minus 0.4 of a weight percent for each pellet and to plus or minus 0.2 of a weight percent for zone averages. The superconducting magnetometer also senses the space between pellets, presence of the getter, and presence of the hold-down spring. MAPS is fully automated, from material handling to data accumulation, data reduction, and data reporting. After magnetic scanning, and still under computer control, the fuel rods are transported to the passive scanning station, where the enrichment level of every pellet is measured, and the total uranium and U-235 content of each fuel rod determined. The uranium sensors are 8 ganged sodium iodide photoscintillators, which sense the natural radioactivity of the uranium and its daughter products. The data from the 8 sensors are combined by the MAPS computer to provide rapid, real-time measurement. The uranium measurements have no known error, and we've shown that unknown uranium errors are much less than 1 gram for each rod shipped. The MAPS computer combines the magnetic and passive scanning data to make a real-time quality decision. The computer then instructs equipment to place each rod in the appropriate output bin. Uranium accountability and billing data are sent automatically to a business information system, and permanent hard copy records are made for audit and for evaluation. The MAPS scanner went into production in 1977, concurrent with the introduction of the BWR-6 fuel design. It was the first industrial use of routine applied superconductivity. The first application of this technology outside of the United States will be in 1982, when a superconducting fuel rod scanner is installed by General Electric for Japan nuclear fuel at Yokosuka, near Tokyo. We've seen examples of how the General Electric Company has created a factory of the future for fuel manufacturing in Wilmington, North Carolina. Modern physics and modern microelectronic engineering have been applied to design and implement automated equipment which combines manufacturing, measuring, and reporting operations into single automated stations. General Electric will continue to invest in fuel manufacturing equipment to assure the quality of BWR fuel while meeting the productivity and regulatory challenges of the 80s.